So, rational inequalities are very similar to polynomial inequalities. There are a couple things that are going to be different. So the first thing that you want to do is find all zeros and excluded values of the function. Okay? Zeros come from the numerator, and the excluded values, those are the values that give you zeros in the denominator. Okay? So if I am looking at this, I should have added up there, everything needs to be moved to the left side. Well, you're really not going to see anywhere you've got to move it yet because we haven't looked at combining any like terms or anything. So they should all be like less than or equal to 0 or something like that to start off with right now. So, so my zeros come from the numerator. And what would I get for my 0 if I've got negative 2x squared? 0. That is x equals 0. Because if I plug 0 in there, it'll make that term 0. And then I'll get x equals positive 1 and x equals negative 2. And then, just like when you were looking for those zeros last night, you have to do the excluded values. And x cannot equal 5. Now, even though it is an excluded value, a value that we cannot have, we still want to put that on our sign chart. So all zeros and excluded values are going to go on your sign chart. So when we make a sign chart, it's going to be just like we did for the polynomials. We want to put these numbers, 0, 1, negative 2, and 5, on our number line. So we'll have our negative 2 here, 0, 1, and 5. Now, I like to go do something like this right here. I like to, I know that x cannot equal 5, so I like to put like an x over that, just to remind myself on my final answer, you can't use a bracket with 5, right? We can't include 5 there. And then we're going to do just like we did for the polynomials, and everything that we have goes over here on the side. Negative 2x squared, x minus 1, x plus 2, x minus 5, and then an answer line. So we're just making a chart very much like we did for those polynomials. You want to include all the terms from the top and all the terms from the bottom. Now, for negative 2x squared, when I plug in a number and I square it, it will make that number positive, right? But then I'm multiplying it by negative 2. So what am I going to get for this whole top line? Negatives all the way across. Because no matter what number I plug in, I'll get a negative 2 times a positive number, which will give me a negative number. All right, then the others are very similar to what we've done before. For x minus 1, you'll have negative, 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 positive, positive. Here we'll get negative, and then I'll switch to the rest positives. And for the 5, we'll have negatives all the way across to the 5 and a positive. Okay. Then we want to look down the line for our answers. 4 negatives will give me a positive. 3 negatives gives a negative. This one also has 3 negatives. That is a negative. We get a positive here and a negative for that last one. Okay. So, for this, Zane, our answer is going to be positives or negatives? Negatives, because we have a less than 0. So we're looking for the negatives here. Now, I have a less than. I cannot, even though negative 2, 0, and 0, 1 are right next to each other, I cannot connect them because I need to be using parentheses here, so I'm going to have -2 to 0. And then I'll have 0 to 1. And then I'll have 5 to infinity. That'll be my answer right there. It actually is not that important that you don't include 5 here because you're using parentheses anyway because you have a less than sign, right? So you weren't going to use a bracket with anything anyway for these. So it's not all that important that we thought about the fact that 5's not a 0, it's an excluded value. But if we have an or equal to sign, it will become more important. We're okay here? All right, let's continue and do another. Okay, now this one is not factored for us, so we're going to have to factor. And that numerator is one of those that's a little bit more difficult to factor, right? So we are going to I'm going to show you guys how I factor, because I do not do X method. X method is fine. It gets you the right answer every time, but you have to know the rules for X method. There's a lot of you that are forgetting to divide back through by that number for that. So I just factor like thinking about how it would multiply back together. So I know when I factor this numerator, I know that to get my first term, I have to get 2x squared. So the only really way I can do that is to do 2x and x. I could do -2x and -x, but don't make your first term negative. That just makes it more complicated. So I got 2x and I've got x. That's my only option. So I know this is going to be the case right here. This right here helps you because if you forget to divide back through on X method, you're going to have x's right there, and that can't be true. That can't be right because when you multiply it back, you won't get the 2x squared. And then for my last term, this one is actually not that bad at all because my last term is -7, and I've only got 2 options for multiplying to get -7. I could use -1 and +7, or I could use +1 and -7, right? So then I just guess and check. The more you do it, you might just be able to do it in your head without actually writing it down. But, like, I'm just going to say, well, maybe it's -1, 7. So if I put -1, +7 right here. When you're checking this, you should already know that 2x times x is going to give you x squared. That's the reason you pick those numbers, right? So you really only have to check these outside terms right here. That gives you 14x. And then the inside term right there is going to be -1x. Oh, I picked the right one, actually. And then that last term, -1 times 7, should give you the -7, right? So these right here, +14, -1, that gives you 13x, which is actually what we were going for there. Now, if that didn't work, I might need to switch where the 1 and the 7 are at, or change signs for that, or sometimes you have more options, like other numbers you could try. So I just reason back through multiplying it back together. You don't have to do it that way. If you use X method, it works as well, but you'll get -14 on top. You'll get +13 is what you want to get when you multiply. You're going to do a +14, a -1 for that, but then you have to divide by 2 there at the end, so you get the 7 here, that's what we got, and then you get 2x minus 1, which is what we got there. So there's just another option for you. If, like X method, you're forgetting and messing up, you may just want to try it like guess and check like I did. Now, that took up a lot of room. I'm going to rewrite this without all the stuff around it. So I got 2x minus 1, x plus 7 over 3 minus x. And that has to be greater than or equal to 0. So now that I have this factored, I want to think about the zeros that go with this. So my zeros here. I know this is x equals -7. What do I get for this one, the 2x minus 1? 1/2, because what you're thinking is 2x minus 1 equals 0, right? So you move the 1 over, 2x equals 1, you divide by 2. And I can tell a lot of you are getting to where you can just do that in your head, but if you need to write it down, write it down. So we got x equals 1/2 here. Be careful with this one right here. What is this is actually not a 0, it's an excluded value. What's this one going to be? 3. X cannot equal 3 right there. Be careful with that one because it's not just the opposite sign because it's written backwards. You're thinking 3 minus x equals 0. And here I would just add the x is what I would do. And then 3 would equal x. So be careful when it's not just in that standard order, right? You also need to be careful on your sign chart here. I'm going to put -7 here, 1/2 will go right there in the middle, and 3 will be up here at the top. Now, it is especially on this one, I'm going to put an X on that 3. Because X is an excluded value, I cannot use a bracket with that 3 right there. Okay, then I'm going to do my sign chart like I'm used to 2x minus 1, x plus 7, 3 minus x, and then the answer line. Okay, so 2x minus 1, if I plug in like negative numbers down here, I'm going to get negatives. Once I get past 1/2, I'm plugging in something like 2, I start to get positives there. For the x plus 7, I'll have negative, and then I'll switch to positive here. Be careful with this 3 minus x. It's usually you start with the negatives first and it switches to positives. But what if I plug in -8 right here? It turns into a positive, right? 3 minus -8 is actually, that's going to be positive. So what happens here is like all these negative numbers, and even if we're plugging in a number like 2, 3 minus 2, still positive, right? So you get positives all the way up to the 0 here, and then it switches to negative. So be careful. That happens a lot whenever we see the number first instead of the letter first on those. And then we're just looking at our chart for this, for our answer line. We got 2 negatives here, that'll be positive. Just 1 here, that's negative. All positives here, and then a negative for that last one. So for this one, Delilah, which ones are our answers? The positives or the negatives? Positives, because we're looking at greater than or equal to 0. So we got positives here. And we have an or equal to sign this time. So we want to use brackets when we can, right? So I would say negative infinity. I cannot use a bracket there because you can never use a bracket with negative infinity or with an infinity. And then, but at -7, I could include that term. So I'm going to use a bracket at -7. And then I will have a bracket at 1/2. But can I use a bracket with 3? I cannot, because 3 will give me a 0 in the denominator, so that has to be a parentheses. That's why I like to put the X on it on the number line, because it's easy to forget that there whenever you get all the way to the answer on that. So this will be our answer here. Okay, questions? I think since we've already done polynomials, these are not going to be too much more if you knew how to do those. Pretty similar to what we had before. So what I want us to do, that's the last one, isn't it? I want us to spend about, we are going to look at vertical asymptotes and wholes today. Yesterday, I didn't specifically talk much about horizontal asymptotes, but the horizontal asymptotes are pretty much what you're doing whenever you do the limit as x approaches infinity or negative infinity, right? Because if your graph sort of levels out at a number, you have a horizontal asymptote there. So today we're going to talk about how we can find vertical asymptotes and holes. And these are the type of what we call discontinuities that rational functions can have. So it kind of reviews what a rational function is there. We have restrictions. Whatever's in the denominator cannot equal 0. We talked about that yesterday. If the denominator equals 0, then we are going to have either a hole or a vertical asymptote at that point. Okay, so down here in this little chart, it says a hole occurs when the factor in the denominator cancels out with the factors in the numerator. What's happening there is you have what would be a 0, but then we're saying, no, that can't be the actual value, so it cancels each other out, and you have a hole at that point. I am going to graph this on Desmos. A lot of these you're going to see are going to be calculator inactive, but if we look at this on Desmos, if I type in f of x equals x minus 1 times x plus 2 over x minus 1. On Desmos, you cannot see holes, or at least not just by looking at the graph. Because what a hole is it's one, at that one single point, whenever x equals 0, your function is undefined. But all the points around it give you a value, right? So they don't show up if you just graph it. However, if you know where to look, I can see in this denominator that x cannot equal 1, right? So if I go over here to where x equals 1, if I can get right to that point, if I click on it and drag it over there, oops, I lost it, then it's going to turn into an open circle and show that that is undefined at that point, right? So holes are tricky to see on a Desmos graph. Now, a lot of them you're not going to be able to use Desmos anyway, but if you can, you still have to kind of know where they're at to be able to find them. Here are a couple ways that you can have holes on a graph. The most common, the one that we probably saw in Math 3, is that your factor, x minus 1, cancels out on top and bottom. Okay, that's what we probably saw in Math 3. You would also have a hole if you have x minus 1 on top and bottom, and you've got a higher exponent on the top than you do on the bottom. Okay, so basically, like here, if we wanted to write that out, I bet it's not going to let me write it well because this is in a table. Let's see if it will. Oh gosh, what's happening here? Let's see if it'll let me write. So like, what we've got here is x, no, it does that weird thing. Let me write it up here. So what we have here is x minus 1 times x minus 1 times x minus 1 over 2 times x minus 1 times x minus 1. That's what we're looking at right here. So if we see this, if you cancel the x minus 1 factors, and there are no more of them left on the bottom, then that is going to give you a hole, right, in the graph. Okay, so you would have a hole at x equals 1. You still have one left up here. That tells you that you have a 0 at 1, but you really don't have a 0 at 1 because x cannot equal 1 for this function, right? So that's what the graph will look like whenever you have holes, and it's going to be shown by open circle, right? For a vertical asymptote, these are much easier to see from the graph. So from the graph, like if I type this in, x minus 3, x plus 2 over x minus 1, x minus 3, x plus 2 over x minus 1. If I look at this graph, it becomes pretty evident that you've got some sort of asymptote going on, right? The vertical asymptotes is when you're going to see that graph kind of go like this. I think this one also has a slant asymptote as well. But like if I type in x equals 1 right here, especially if you zoom out, you can see, oh, we're just getting closer and closer and closer and closer to that line, right? So they're a lot easier to see from the graph. In this case, vertical asymptotes, holes, these discontinuities always come from the denominator here. So we can have this scenario where you just have this x minus 1 and nothing in the top cancels with it, so that gives us a vertical asymptote. We also could have this scenario, I'll write it up here, that g of x would be x minus 1 times x plus 2, and in the denominator, x minus 1 times x minus 1, right? Kind of like we saw in the other. These will cancel, but this time you're left with an x minus 1 in the denominator, right? So, yes, these canceled. There was supposed to be a hole at 1, but there's also supposed to be a vertical asymptote at 1. And vertical asymptotes sort of trump holes there. So if you have a place where there is both a hole and a vertical asymptote, it's just a vertical asymptote for that. Okay, does that make sense? Okay, here. Now, here is what we have not done. So in Math 3, you talk about holes and vertical asymptotes. Oh, there's one more thing I want to add too. Let's just squeeze this in wherever you got room. A hole is also sometimes called a removable discontinuity. It is called a removable discontinuity because you can remove it by just putting like 1 point there, right? It only takes 1 point to get rid of that discontinuity. So you might see that phrase removable discontinuity thrown out there to mean hole. They're interchangeable. Non-removable discontinuities for rational functions, it's just going to be vertical asymptotes. But it does also include jumps in the graph. Those typically show up on piecewise functions. We'll see those later. You won't really see them here. A vertical asymptote is sort of like a jump in the graph, though, like you jump from positive infinity back down to negative there. Okay, so we have to do some limit notation with this. This limit notation is going to be a little different than the limit notation that we used for end behavior. Okay, so often we want to talk about what happens at the discontinuity, and we can use limit notation to talk about that. Okay, so whenever I see the limit, right here I've got x approaches 1, and then there's a negative behind the 1, right? So when I have limit as x approaches 1 and the negative is behind the 1, that does not mean x approaches negative 1, right? We can't just throw the negative behind a number because we feel like it. When I see this, the negative behind the number, this means the limit as x approaches 1 from the left. That's what we're talking about here. So that negative behind the 1 means that we're looking at what's happening at 1 from the left side. So if I go to my graph and I look where x equals 1, that's right here. I'm going to draw myself like a dotted line, although it's going to do some crazy stuff here probably. Maybe it'll still kind of look like a dotted line once it crawls down the page there. For that, at positive 1, if I approach from the left-hand side, so I trace my graph, left hand jumps up here. As I get closer and closer and closer to that vertical line from the left-hand side, I go to this point right here. The y coordinate of that point is my limit. Okay, so the y coordinate there is 3. Now at holes, it doesn't matter that you have an open circle because a limit doesn't say that the function equals that value, right? A limit says we're getting close to that value, right? So as I go here, my y values are getting really, 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 really close to 3, even though at 3 the function is undefined. For a hole, you should have the same limit from the left and from the right. To show that you're talking about a limit from the right, you put a positive behind the one like this. So this is the limit as x approaches 1 from the right-hand side. And at a hole, you should get the same number for both sides, right? Because if I approach that dotted line from the left-hand side, I also go to that single point right there, right? And the y coordinate of that point is 3. Okay, limit notation we definitely didn't throw out there whenever we were talking about holes and asymptotes earlier. Now, let's talk about limit notation for this graph, okay? We're still looking at x approaches 1 from the left and x approaches 1 from the right. At 1, for this graph, it's this dotted line that's really already shown there, right? We are looking at what happens as we approach from the left. So as I approach that dotted line from the left, what is happening to my y values? They are going down, 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 down forever, right? That graph keeps going down. It gets a little closer to the line, but just keeps going down. So I would get negative infinity. Whereas if I approach from the right-hand side, if I go from this side, as I get closer and closer and closer to that vertical asymptote from the right, my y values go up, 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 up to positive infinity for that. Okay, questions there? Okay, let's do some problems. All right, so for these, you're telling me about holes and vertical asymptotes. Holes and vertical asymptotes always come from the denominator, right? So what we want to do is we want to look at the, oh, that's not supposed to be the pen. Okay, we're going to look at the denominator. That's where we find holes and vertical asymptotes. So I'm going to have a hole or vertical asymptote at x equals negative 3 and a hole or a vertical asymptote at positive 5. Right? For sure, I have some type of discontinuity at both of these places because if I plug those numbers in, I get a 0 in the denominator. Okay? One of these is going to be a hole. Which one? Negative 3, because these two would cancel. So right here is my hole. And then the 5 does not cancel, so that is my vertical asymptote. So if I'm going to do B, I'm going to look at the denominator. I am definitely going to have some type of discontinuity at x equals 2 and x equals negative 1. Okay? I have to decide what type. Now, I have things that are going to cancel in both places here, right? The x plus 1s and the x minus 2s both cancel, but both of these are not holes, okay? Because what I'm looking at, sometimes it may be helpful to write it all the way out. X plus 1 over x minus 2 times x minus 2, right? And then on the bottom, I've got x minus 2 times x plus 1 times x plus 1. So if I cancel my x minus 2's, I can only cancel one of them. Do I have any more x minus 2's left in the bottom? I do not. So this one is a hole, because all of the x minus 2's from the denominator canceled out. I can do the same with my x plus 1's. I can cancel an x plus 1. Do I still have an x plus 1 in the denominator? Yes. So that means that I have a vertical asymptote at that point. So if your factor remains in the denominator even after canceling, that is a vertical asymptote. If that factor does not remain, then you're talking about a whole. Okay, and of course some of these we're going to have to factor because they're not going to be factored for us like we see on C. This one is not exactly our typical factoring. I can't do anything to the numerator. What could I do to the denominator? I could take out the x, so I could take out an x. Now I've got x squared plus 4. I could, does x squared plus 4 factor into what? Okay, x plus 2, x minus 2. If I multiply that back, I get x squared minus 2x plus 2x minus 4. That's going to be x squared minus 4. So this does not factor into x plus 2 times x minus 2. Let's try that. But this isn't going to work because here we'll get our x squared. Then I get a positive 2x and another positive 2x and a plus 4. So that's x squared plus 4x plus 4. So that also does not factor to x squared plus 4, right? So that doesn't factor any further. But what you can do to check, although we're going to see something happen here. So I know x equals 0 is definitely going to be either a whole or vertical asymptote, but does anything cancel with the numerator here? No. So that has to be a vertical asymptote. So what I can do for this x squared plus 4, since it won't factor, is I could say x squared plus 4 equals 0 and try to figure out what would give me 0 here. If I subtract 4, x squared equals negative 4, then what do I have to do? Square root. Uh-oh. What's wrong with that? Can't square root a negative. I'm going to get an imaginary number for this. Imaginary numbers don't show up on the graph, so that's not going to be a whole or a vertical asymptote. So you get nothing from that. There's only a vertical asymptote at x equals 0. Okay, questions there? All right, let's take it a little further. Let's write some limit statements for this. Okay. So, for all of these, they have asked us to do a right limit and a left limit as x approaches 2. So, like if we wanted to go ahead, we could just write limit as x approaches 2 from the left of f of x, and we could write the limit as x approaches 2 from the right of f of x. Okay, that's going to be our form for our answer. Now, at x equals 2, I need to decide if I have a whole or a vertical asymptote. X equals 2 is in the denominator here, so I have a discontinuity there. Is x equals 2 going to be a whole or a vertical asymptote? Vertical asymptote, right? So, at a vertical asymptote, your graph can go like this, it can go like this. Both sides could go up, both sides could go down. But your answer to these two are going to be positive or negative infinity. We have to know which one, though. And they are not going to let us use the calculator on these. So we have to have a way of coming up with the answer for this. So what we're going to do is if our graph goes to negative infinity, then that means we've got negative values at on that section, right? Or if our graph goes to positive infinity, that means we got positive numbers on that section, right? So we can do a sign line kind of like we chart kind of like we did for our positives and our negatives, right? So I would have x equals 1, x equals negative 3, and x equals 2 will be my zeros and my excluded values. So I will put them on a sign line. So I've got negative 3 here, positive 1, positive 2, and then I've got x minus 1, x plus 3, my x minus 2 up here, and then my answer zoom here. Okay, so for the 2, I'll have negative, 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 positive. For the 1, I'll have negative, negative, positive, positive. For the x plus 3, I'll have negative, positive, positive, positive. And then so for my answer line, I will get negative, positive, negative, positive. Now, unlike our sign charts that we did on like the last part, we're not looking for like where the graph is positive or where the graph is negative. What we care about is what is happening right here at 2. Okay? On the left side, as we approach 2 from the left side, so we're talking about this piece right here, is our graph going to go to positive or negative infinity? It's going to have to be negative infinity because the values there are negative, right? And you can't go to positive infinity if the values are negative, right? So when you know there's a vertical asymptote, the answer is infinity. It's not going to be a number, right? But the left side right here is negative, so that tells us that our left statement is going to be negative infinity. And then on the right side, I've got a positive. That tells me my right side statement is going to be positive infinity. Does that make sense on that? Okay. B is going to be different because at x equals 2, which is the only one we are told to care about, right? We got the limit as x approaches 2 from the left of g of x. That's what we're looking for. And then we also want to know the limit as x approaches 2 from the right of g of x. So there is going to be a discontinuity of 3. You have a vertical asymptote at 3. But they're not asking us to write limit statements for that. They're asking us to write limit statements at x equals 2. What's going on for this graph at x equals 2? What kind of discontinuity do we have? There's a hole. All right, so here's what you're going to, when you have a hole, you should get a number answer. Okay? So here is what you're going to do. This is sort of like some solving limits. You can do the limit as x approaches 2. You don't have to put the plus or minus because it's going to be the same from both directions at holes. Of x minus 2 over x plus 4 over x minus 2 times x minus 3. And you can just cross these out. They're going to cancel each other out, right? And then you can plug your 2 into what's left, right? So plug 2 in here, 2 plus 4, and then 2 minus 3. All right, so I'm just plugging in whatever value you're approaching to whatever's left, and I will get 6 over negative 1, so I get negative 6. At holes, you'll get the same number for the left statement and the right statement because you should be approaching that same point. So let's summarize right there. At holes, cancel, and plug in the x approaches to for your x. Okay, everybody good here? All right, let's do this last one right here for C. I'm going to have at x equals 2. Do I have a hole or a vertical asymptote here? That is going to be a vertical asymptote because one of the x minus 2's does cancel, but there'll be one left in the bottom, right? And then I would also have a vertical asymptote at 1. And then I've got zeros at x equals 4 and x, well, do I have a 0 at x equals 2? I was about to write it down, but I don't because there's actually a vertical asymptote there. So I need that for my sign chart because I need to be doing the limit as x approaches 2 from the left of h of x, and the limit as x approaches 2 from the right of h of x. And because I know there is a vertical asymptote here, the answer is positive or negative infinity. I just have to choose which one. So I'm going to do my sign line. I will have 1, 2, and 4. I will do x minus 4. Now, this is a little tricky right here. You can either list x minus 2 twice, or you could put those x minus 2's together and have x minus 2 to the third power. I feel like that might be a little confusing though, so I think I'm just going to do this. I'm going to just do x minus 2 right here. Then we'll have an x minus 2 squared and an x minus 1. And I've about ran out of room for my answer. I may have to put it below the graph on this one. I'll put my answer down here on the bottom. So for the 4, I will get negatives all the way across except for the last one. For the 2, I'll get negative, negative, positive, positive. What do I get for x minus 2 squared? What? Okay, it's going to be either positive or negative all the way. Which one's it going to be for this one? You can just like pick a number. Like if I plug in 0, I got negative 2 squared. Negative 2 squared is positive 4, right? So positives all the way across. What will cause you to get a negative all the way across is if you've maybe got like a number out front, like that's like a negative 2 times this stuff right there. And then I've got negative, positive, positive, positive. So I'm going to put my answer actually here below the line. I'll get negative, positive, negative, positive. Now, I'm not like giving an answer of where this is positive or negative here. All I care about is what's happening at 2. On the left side of 2, is my graph going to approach positive infinity or negative infinity? Positive. I'm pointing to the wrong spot. Positive, because my answer there is positive. So I'll have positive infinity from the left side. How about from the right side? Negative infinity. Technically on those charts, you could leave 1 and 4 off because you only really care about 2. But I find it easier to do the chart if you just do it like we've already been doing. Not throwing something else crazy there. Alright. So, we're not going to have time to do all of this here. But they are asking you for some different things. So, let's just look at A real quick. They want the limit as x approaches 3 from the left to be 5, and the limit as x approaches 3 from the right to be 5. That's probably going to be a hole at x equals 3, right? And then where are you going to have vertical asymptote for this one? If the limit as x approaches 1 from the left is negative infinity, and limit as x approaches 1 from the right is positive infinity, that's going to be vertical asymptote behavior. Positive or negative infinity is telling us vertical asymptote. So we got a vertical asymptote at x equals 1. So I know, like, if I want f of x here, I know I need a x minus 1 in the bottom that does not cancel out. I need an x minus 3 in the top and bottom because I need those to cancel so I get a hole. Now this will take care of my vertical asymptote. However, I will not get 5 if I plug in 3 right here, right? So if I think of like the next step on that, the limit as x approaches 3 of x minus 3 over x minus 1 times x minus 3. If I cancel these, I'm going to put a 1 right here, and then plug in 3, I get 1 over 3 minus 1, which is 1/2. But what am I supposed to get? Supposed to get 5 right here. So the way I can fix this is I can put a 10 right here. Because if there was a 10 in front of this, instead of just a 1, then x minus 3's would cancel. I'd plug in 3. I'd have 10 over 3 minus 1. And 10 over 3 minus 1 would give me 5. So this is a possibility. There's some other things you could do, but this will be maybe like the most simple one that you could do. And we're going to be out of time for that sketching a picture there, but hopefully